In this video, we'll be discussing a dynamic guidance model for the aircraft. We use the word dynamic, again, because we're going to be directly incorporating two of the forces that act on our system. So we'll consider course angle and flight path angle in terms of the lift, and we'll consider the ground speed changes in terms of the thrust. So let's go ahead and get started. So we have these two relationships that we can deal with. First, from Newton's second law, we can derive that the ground speed velocity derivative, in other words, our acceleration, is just equal to the force of thrust over mass minus the force of drag over the mass minus g times sine of our flight path angle. Excellent. So that comes from, we have Newton's second law. Excellent. So we'll utilize, again, we have forces. So now this becomes a dynamic equation. So we have our thrust force and our drag force that come into play. We also have our coordinated turn model. And we're going to express this in terms of our load factor. So we have tangent of phi, which we know that tangent of phi is equal to the sine of phi over the cosine of phi. And if gamma dot is equal to 0, right, so we're moving upwards at a constant or near constant angle, then we derived a relationship in a previous lecture where we mentioned that our load factor is equal to the cosine of gamma all over the cosine of our bank angle, of our roll angle. Right, so we have this term here that we have a 1 over cosine of phi, right? So we can solve for that 1 over cosine of phi term. It's just going to be equal to the cosine, the load factor divided by the cosine of gamma. So again, this is the assumption made here is that 1, gamma dot is equal to 0, and 2, we're assuming a coordinated turn. Okay, so that's where we go from this tangent of phi to call the 1 over cosine of phi is just equal to the load factor all over the cosine of gamma. Excellent. So now we have, again, we have this the definite, not that relationship. The definition of our load factor is actually just the force of the lift over mass times gravity. Plug that in and simplify. We have F lift over mass times our V sub g times sine of our roll angle over the cosine of our flight path angle. Excellent. So now we can define our course angle derivative in terms of lift force, which is pretty smooth. So we have two relationships that now have a relationship of force defined in it. Okay, so that'll allow us to write down our dynamic guidance model from using the similar approaches we did with our kinematics guidance model. And again, I want to point out here that there was a cosine term left from a previous iteration of the book. Perfect. So now our inputs end up affecting our ground speed velocity, our course angle, and we have our flight path angle. So those are where we see the inputs of our system. And we're going to treat our inputs. The system will have thrust, and we're actually going to have our CL be defined as one of our inputs. So this lift then goes into that component and that component, and the drag, so this is our linear drag model. It affects the force of our drag, and we have F drag go in there. And we have assuming that our airspeed is somewhat constant. Okay, so now we have if we write down our states of our system and our inputs, then our states are just going to be our Pn, Pe, and H as before. Then we'll add in a state of Vg. We'll have our course angle and our flight path angle. And then our inputs to the system are then F thrust. And we'll say that we can have our lift coefficient as one of the inputs and our roll angle. Okay. Just a sec. Sorry, I had a couple things wrong. We're going to just assume that our bank angle is the input to the system. So we see that our bank angle shows up. Let's see if I can highlight it. We'll see that our bank angle will show up there and there, right? So our bank angle shows up. It's one of our inputs. The other thing that I stated incorrectly was that our airspeed was somewhat constant. We don't have to have our airspeed constant because we're changing Vg, but we can compute our airspeed from this relationship right here. And that's just utilizing the wind triangle. So, and also, again, if we need our heading angle can be derived from our course angle as such. And I just noticed that there's a typo here. This should be our heading angle, as it always has been. Right, so we have our heading angle relationship that we can define here, so that'll help us with our north and east time derivatives. And we have the relationship of our airspeed given our ground speed and our this should, I think, also be our heading angle right there. Okay, so we had a couple errors there, but I think we've got them all figured out. Anyway, so that gives us a dynamic guidance model. And I'd also previously misspoken on our final kinematic model. I'd said that this was a model preferred by pilots. That's actually this dynamic model is preferred. So the book mentions that this models the aircraft in a similar response / inputs seen by a pilot, which they're normally, I'm not a pilot, but speaking from the book, they can normally control the aircraft in terms of thrust, the lifting surfaces, and the bank angle. So apparently this dynamic guidance model is one of the reasons it's nice is directly for that. Okay. One final variation is if we have the no wind, right? So our the time derivative of v sub g is replaced directly with the time derivative of v sub a. And then everything else is pretty much the same. Oh, and we have we have the relationship with our course angle or our heading angle instead of our course angle. So there you have it. Now we have developed both kinematic and dynamic models, and we also developed the Dubin's model, which is a form of a kinematic model that we can use for higher level planning. And we've highlighted all the assumptions so that you can utilize the appropriate model given the expected conditions.